Hello physics students. So today you're going to learn about Ohm's law, which tells you the relationship between current, resistance, and voltage, the three basic parameters about an electric circuit. Now I don't want to just tell you the relationship, I want to show you with some demonstrations. But I'm at home right now, so what that's going to mean is a lot of time travel, just so you're aware and you're ready for it. So Ohm's law, here are the three ideas. I just want to remind you, in the last video, we learned what current was, symbol I. It's the chain delta Q over T, how much charge flows past a cross-section of wire divided by the time, the coulombs per second or the amps. You could almost think of it as like a velocity of charge, how rapidly charge is flowing past a point. Then we learned about resistance, that current doesn't flow with no restriction through wires. Because the electrons are bumping into atoms, they are sort of like delayed or like it's kind of like a friction effect. That is quantified by the symbol capital R. We learned the formula, resistivity. It's a constant on the reference table. Depends on the metal that the conductor is made of. Length on top, meaning longer wires make more resistance. Area on the bottom, which means that thicker wires mean less resistance. And this, the unit of resistance is in ohms. Now, I didn't get a chance to show you actual resistors. I mean, we looked at wires, but at school, I have some actual resistors that are purchased, commercially available resistors. So what I want to do is send you back to the day when I was back in school so that you can see what an actual resistor looks like if you were to buy one. So our first time travel, brace yourself, here we go. Let me show you some commercially available resistors. So a lot of the resistors you buy will look something like this right here. See this little line, and it's got got a bunch of colors on this little ceramic piece right here. And you could look up online how to read these colors. There's a code to it, and you could figure out the resistance of this resistor just from the colors on it. Now, you could buy resistors like this that are 10 ohms, 1 ohm, 1,000, 1,000,000 ohms, and they'd all look pretty much the same. It's what's inside that makes the resistance. So a lot of resistors look like this, pretty small little ceramic things. Sometimes if they have a pretty small resistance and to allow them to have more current in them, they can be a little bit bigger. Okay, so that's a possibility. And sometimes you can buy resistors that are made in ceramic material if there's a lot of current going through. So this is a resistor that I have for a lab in Regents. So this is approximately 10 ohms in this, and because it can heat up so much, it's got all that ceramic material. So you see a couple different kinds of resistors. All right, so that was, there were some examples of resistors. And then in a circuit, we need a voltage source, which a reminder that in the Regents, they often use the word potential, which means voltage. And a reminder again of what voltage is. We learned in the last unit that it's a certain amount of work that's done on a charge. So it's a joules per coulomb that's on a single electron. I mentioned in the last topic that if you had a battery like this and it's 1.5 volts, if you take a single molecule out of that, so tiny you can't even see it, that chemical reaction maybe sends one electron from one atom to another. It's 1.5 volts. Even though it's one atom, it's not like a fraction of 1.5 volts. So it's like a pump, a thrust on every single electron that we call voltage or potential. And of course, batteries come in different sizes. I have here a AA battery and a D cell battery, but you can have AAAs like in a calculator, C like in some toys. And they generally look like this cylinder here with a button on one end. This end, the button, is the positive side. This is the negative side. So battery always has two terminals. I mentioned this and I repeated it a lot, that voltage is always two prongs. And so that is denoted by the two sides of the battery. But we don't draw batteries like this in a circuit when we're doing physics problems. We draw a schematic of a battery. And so the way a battery is drawn is 4 lines, small, big, and then this is like the wire coming in. This is the wire coming in on this side. The small terminal here is the negative side. The large is the positive side. And that's how we draw a battery in a circuit, not like this. So let me create a pause to allow you to copy these notes down. Okay, moving on. Sometimes you can have multiple batteries powering one device. There are 2 general ways you might be able to hook batteries together. One is what we call series. It's achieved by just stacking 2 batteries on top of each other. Not the button to button, but the button to the flat side, and this is now a series arrangement. I made a little space over here just between these because just so it's a little clearer when it's drawn what's going on. But there is no space. There's just a contact. Now, again, we draw these not like this in a circuit. We would draw battery 1, battery 2, battery 3, basically 3 of these in a row. That's the key idea of a series arrangement of batteries. They're in a row sequentially. The reason why devices do this is because then what happens is the electrons get pumped not just once through one battery, they get pumped through 3 batteries. Pump, 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 all sequentially, so you get more voltage. These 1.5, 1.5, 1.5, the total voltage out of there would be 1.5 plus 1.5 plus 1.5, which is 4.5 volts if you stack 3 batteries end to end like that. So that's series. You could also arrange batteries in parallel. What you would do is you would put them next to each other like this, button on top, all the buttons on top, and all the flat ends on the bottom, and then you take a wire and you connect all the positive sides and you connect all the negative sides. So how would you draw that schematically? You would draw it like this. Here's one battery, another one, all the positives connected with wires, and then the wire continues. All the negatives connected with wires, and then the wire continues. This does not up the voltage. What the total volts of this arrangement is just equal to the voltage of the individual batteries. In other words, if these are all 1.5, the total is 1.5. And you might be saying, well, why would you bother if you're not getting any more voltage to put more batteries in? Well, imagine, like, why would a car have 2 gas tanks or 3 gas tanks? Well, you want to go farther, right? So that's why you use batteries in parallel. One of the reasons is you might want the device to last longer before it runs out of battery power. So that's series in parallel. Now, let's hold off on this. Let me pause, give you a chance to copy these notes down in your notebook. All right, now an example. I have here a calculator. So this, of course, runs by multiple batteries. I'm sure you've had to change your batteries before. And you see that there are 4 batteries in this back of the calculator here. And it looks like they might be in parallel. If I was in class, I would ask, how many people think these are in series? How many are in parallel? It's a trick question. Everyone puts their hand up in parallel and they get it wrong. They're not in series. They're not in parallel. They're in series. You may notice that these batteries have to be installed alternating. Notice the positives here, then the positives here, positive here, positive here. If you were to take the plastic apart, you would see that these are connected with wires like this. And so the device has them in parallel because the batteries are pumping the charge sequentially one after another. So whether something is in series and parallel is not necessarily the shape of how it's arranged, but electrically how it works. These pump one after another, so the calculator then can run off of 1.5, 1.5, 1.5, 1.5, or 6 volts. That's why. And the reason why they put this is just like this instead of end to end is a space-saving feature. You wouldn't want this calculator to have a little extra nub over here because the batteries have to be 4 in a row, right? You want them compact, so that's all. Okay, so that's batteries in series so that the calculator can run off of 6 volts, which is what it requires. Okay, so, I'm not, for my demonstrations, I'm not going to be using batteries to figure out Ohm's law. what I'm going to be using is an electronic power supply that allows me to adjust the voltage. So I'm going to send you back so that you could see me explain how the power supply works. So brace yourself. So before I show you the workings of Ohm's law through a circuit, I first want to show you some basic important points about circuits and how they operate. So what I have here is a power supply. We used it in the mapping labs already, and a voltmeter. And so I'm going to turn this on, and the nice thing about this is, unlike batteries which work with a chemical reaction, which produce a certain voltage based on the chemicals inside the battery, this can be adjusted to any voltage I want. So what I'm going to do is turn this up to about, you see, I could go 5 volts, I could go 14 volts. I'm going to make about 5 volts on the voltmeter right here. And the other thing I want to point out, an important thing, is that voltage is always 2 prongs. Okay, so I cannot get that voltage by just plugging in one wire into the power supply. You see, now I get 0. You say, well, you plugged it into the black one. Plug it into the red one. That's the positive. So, all right, let me plug it into the positive, and I still get no value. Remember, voltage is the joules per coulomb when an electron moves from one point to another, or the electric field integrated from one point to another. But again, that implies 2 points, a starting and an end point. So I need 2 points for voltage. But connection to both sides to get voltage, one is not enough. This is why every cord has at least 2 prongs to it, right? So there's 2 prongs. Cut one of these off, and the appliance will not work. Whatever one you cut off, you plug in just one, it's not going to turn on. Okay, so that was how you saw the power supply. It still needed 2 prongs, a positive and a negative, but it was just with wires so that I could have a dial to adjust the voltage. Now, what I'm going to do is show you how I can use that power supply to make a very simple circuit, the simplest circuit that you can create. So I'm going to show you how that's done with just a light bulb, the power supply, and some wire. So brace yourself. Let me send you to that demonstration. So now I'm going to take this away, and I'm going to connect this circuit with a light bulb. And again, that idea of 2 prongs necessary. So if I connect this bulb like this to the positive, it doesn't turn on until I complete the circuit. You always need like a circle with current. Different than water, which is why I have the sink here in view. If I turn this faucet on, all that's coming out is like one pipe, and it doesn't need to flow in a loop. The water can squirt out just fine. But if I do that with electricity, the electrons will not squirt out the end through the light bulb. If this worked with a paddle wheel and hoses, I could put the hose like this and have it go like into the lawn, and then the water would go through and turn this paddle wheel, turn the light on in a sense, but not with electricity. You need the loop. Okay, so that's the first point. All right, so this is, now what I want to do is, you'll copy these down. This is how you would draw that very simple circuit that I created with a bulb and the wire and the power supply. Simple circuit. You have some voltage source and possibly a resistor. And remember, I mentioned this in the last video, the way you draw a resistor schematically, even though they're like little tiny cylinders, you draw this zigzag line, okay? By the way, in the demonstration, I had a light bulb. If you wanted to draw a light bulb instead, you would do a spiral like this, surrounded by a circle, and that would be like the glass bulb and the filament in the 2 sides of the bulb. You don't have to remember these symbols, by the way, because they are also in the reference table. So let me come forward, show you. I'm in the electricity section on page 4. And as you can see down here, you've got a bunch of symbols. It shows a battery right here. You could also draw a battery with just one pair of lines. It's like a cell of a battery. Switches we'll talk about, voltmeters, ammeters. But here's the resistor, and here's something called a variable resistor. which actually I'm going to show you in a demonstration what a variable resistor is. And here's the lamp or bulb, okay? So again, in the electricity section, you don't have to remember how to draw these things. You can just use your reference table. All right, so go ahead and copy this down. I'll create a pause for you to do that. All right, so now we get to Ohm's law. The main idea of today, the main idea, the biggest idea of this entire unit. So important, here it is. It relates current, resistance, and potential. So Ohm's law, I started writing a formula over here. I created a fraction because we want to see how current's going to be affected by voltage and resistance. And so maybe one makes more current, maybe one makes less current. So remember when we studied Newton's second law, and you don't have to write this down, we had A equals F net over M. And what that meant is more force meant more acceleration. So we put force in the numerator to represent that mathematical property. More mass meant less acceleration. So we put it in the denominator so we would divide by the big mass to make less acceleration. So possibly voltage and resistance, one's in the top, one's in the bottom. Maybe they're both in the top, maybe they're both in the bottom. Well, we're going to see that in a demonstration. So the first thing that I'm going to do is send you to see where voltage belongs. Now, maybe you already know. It's kind of common sense, but you're going to see it in a demonstration. So here you go. I'm sending you to see that relationship. So now what I want to do is I want to make a circuit that could tell me how voltage affects the current in the circuit. And then I'm going to make another circuit to demonstrate how resistance affects the current in the circuit. So this measured voltage, but how do I measure current here? Well, what I could do is I could take one of these multimeters and I could insert it within the loop. So I'll turn it on, and instead of the electricity returning the power supply, I'm going to plug it in right here and then make it go to the power supply. And what that does is it puts the ammeter within the loop of the circuit. It's like a high-speed toll booth on an interstate. The electrons will register as they pass through this. It doesn't resist the flow. It allows it to pass, and it records how much current I have. So now I've got a measure of the current, about 0.4 amps, as you could see from this meter. And then I want to measure the voltage at the same time. So I'm going to just put this on top here, right on top of these wires, and measure the voltage at the same time. So what I have here is voltage and current. And so what I'm going to do is start down low. And I see that for 0 volts, I have 0 current. But if I put a little bit of volts, let's say 1 volt, about 1 volt, I get 0.23 amps. Let's try 2 volts. More amps. More volts, let's go to 3. And I get more amps. These are going up together. Up to about 5, and I'm up to 0.43. So that's the first pattern we're seeing. More voltage, more current, okay? Now, you could also see that from the brightness of the bulb, right? So this bulb brightness is actually related to the current coming through the bulb. All right, so we saw more volts, more current. So just like we had, I erased it, I probably shouldn't, A equals F net over M, more force, more acceleration. So we put F in the top, okay? So more volts, more current. We put voltage in the top like this, okay? Now, mathematically, that means since it's to the first power, if we were to plot current and voltage together, we would get a straight line like this. Oops. Well, I try to do it straight. So what that means is if you double the voltage, you will double the current. If you triple the voltage, you'll triple the current. That's the graphical pattern of that relationship. There's the formula pattern. But some of you who are very observant, very critical in terms of your observations, may have noticed that when I doubled the voltage, the current didn't actually double. And the reason why is because this is the simplest case. When you have a pattern like this, it's called ohmic or ideal behavior. But what eventually happens when you keep cranking the volts up, the resistor gets hotter and hotter. If I touch that bulb, I might burn myself. And so what happens, one of the other things that's actually not in this equation is the temperature dependence. When materials get hotter, the resistance goes up. And so with more resistance, the pattern doesn't continue like this. It actually means you start getting less and less current like this. So it starts to curve. And this pattern at the curve is called non-ideal or non-ohmic or non-ideal. So it really happens in real life. It's not so much of the Regents curriculum, but it is required that you know more temperature, more resistance, even though it's not in that formula. So you do need to just know that as a concept. Now, why is that the case? Remember, electrons are trying to work their way through atoms. So imagine I'm walking through a crowded hallway. That'd be like me, the electron, and the people in the hallway are like the atoms. So I might bump into somebody and then I have to step to the side and I keep going, right? People are in the way. What happens if people are dancing vigorously, spinning around, flying around? That's like temperature. When material's hotter, the atoms are zipping around, vibrating more. And so now that electron's trying to get through when the people are flying around or the atoms, it gets bumped even more and it's harder to get through when things are hotter because the atoms are moving and vibrating more. So again, that's just the concept you need to know. But mostly today, we're just looking the simple where the situation is ohmic. Now, the next thing, where does resistance belong? Maybe more resistance is more current, and so we put it up here with the V, or maybe more resistance, less current, and then like mass, it belongs in the bottom. So again, I'm not going to just show you or tell you what the relationship is. I'm going to show you with a demonstration. So here we go. Now what I want to do is see the effect of resistance. So I'm going to reconfigure this circuit because I already learned one idea in Ohm's law, more volts, more current. But now, how can I change the resistance? Well, one ingenious device is this device right here. What it does is it basically creates what we call a variable resistor. If I hook wires here and here, there's very little resistance because the electricity can just go through this post down to this point right here. But if I go like this, the electricity now gets deposited at this contact and has to spiral through all this wire before completing the loop. So by sliding this, I force the electricity to go through more wire or less wire, more resistance, less resistance. So I'm going to insert that into the circuit now. So give me a moment. I guess I don't have the right wires. I guess I could hold it. Yeah, it might hold. And here we go. We see this is very little resistance, and I'm going to add more resistance, and you see the bulb brightness goes down. So more resistance, we would have seen less current if I had the ammeter there. We see that through the bulb brightness. More resistance, less current, more voltage, more current. So now we're going to put those together into an equation called Ohm's law. All right, so what you saw is when I made more resistance, the bulb got dimmer. In other words, more resistance, less current. So that means, just like mass, R belongs in the bottom, in the denominator. So there is Ohm's law. And as I said, I didn't even need to show you demonstrations. If I had asked you before, do you think more voltage makes more current or less current? Most people would say, more volts, boy, that's going to make more current. And they'd put it in the top, they would be correct. Then if I asked you, does more resistance cause more current or less current? Well, resistance can kind of hold it back. It means less, more R, less I, denominator. So this is very much common sense. Now, graphically, the way we would show that pattern, more resistance, less current, a lot of people want to put a straight line like this. And this happened during Newton's laws. When you had A, mass, they'd put a straight line. It's the descending curve. If you don't believe me, you could just go on your calculator and plot y equals 1 over x, and you'll see a graph that goes down and approaches the horizontal axis, okay? All right, so let me create a pause so you could copy this down. Okay, so now this is also on the reference table. Let me show you where. Ohm's law. It's right here. And it doesn't look like the equation that I wrote. I wrote I equals V over R because that makes more common sense. This is not as intuitive. So, of course, cynical me says that's why they put it this way on the reference table. But if you multiply I to this side and divide by R, you see that you get the same equation. So when you're doing Ohm's law's problems, you always have to write a formula like in everything in Regents. You could start by writing this formula down or the one that I wrote on the board. Or sometimes in books they write it V equals IR. If you multiply the I to the other side, you get V equals IR. That's fine too. Any version of the formula, as long as it's algebraically equivalent, is acceptable. All right, so now examples. I'm going to skip over examples because on tonight's homework, all you're doing is you're taking this formula and you're given 2 out of the 3 variables and you solve for the third. So, I don't think I have to do any examples other than explain the concepts. All right, so I hope you understood everything about Ohm's law. It makes sense. And I hope you enjoyed the demonstrations and the knowledge. And I'll see you in the next physics video.